outward from a positive charge. And if my object wasn't positive, if it was negative, it would also fill the space around it with an electric field. And what direction would those field lines point? Inward. So electric field lines point the direction a positive charge would go if it was sitting at that location. Another way to think of it is that they originate. Electric field lines originate. They start on positive charges. They terminate, they end on negative charges. And these field lines help us to visualize what's happening. Are there really electric fields that look like this? I don't know. It's a model we have that helps us figure out how these objects are interacting. It helps us figure out how the world works. So it's a model that we have, and it works pretty well. But we have to have some rules, right, to draw these field lines so that they're helpful. So what we're going to do is a little worksheet here, help us figure out what the rules are for drawing electric field lines. There are 3 charges. 2 positives and a negative. And the first thing we're interested in is just what direction is the electric field pointing. They've drawn in the electric field lines. They originate on positive charges, terminate on the negative charge, and they want to know what direction do they point at each of these locations. What's the first thing you notice about this worksheet? What did they mess up? They got east and west backwards, didn't they? You can correct that. This is west. That's east. Okay. So if you were standing at point A, what direction would you say the electric field is pointing? What is it? Which one? Yeah. Point A, it's right here. South, southeast, southwest. They've drawn the field line for us. Does that help? Why would it be south? Because it's tangent. Yeah, so they've drawn in the field lines for us. And if we're at that location, picture maybe a gravitational field and you're standing there with your compass. What direction was your compass needle point? If you were, if we draw the Earth and we try to draw some magnetic field lines, this would be the north pole of the Earth and this would be the south pole of the Earth, right? And we have these magnetic field lines that kind of go around like that. And if you're standing here, what direction is your compass point? It points along tangent to the field line. So the field lines are drawn curved to give us an idea of what they're doing overall. But if you're standing at that location, the field is actually tangent to the line. Sort of like something moving in a circular path. We might say something is moving like this, but when it's right there, what direction is it going? When it's right there, it's actually going in that direction, isn't it? And some instant later, it's over here. It's actually moving. Its velocity at that instant is like that, right? So even though it's moving in a circular path, at any instant, the velocity is really tangent to that path, right? The instantaneous velocity. So it's sort of similar with these. All right, so at A, what direction? South. We good with that? At B, south, it points tangent. Where are we? C. D, north, tangent to those lines. E, where's E? Oh, E is up here. So it's going sort of straight out, right? What is that? North. F. G. And H. Okay. So far, so good. Let's turn it over. So I've already told you the answer to the first one, didn't I? It says electric field lines originate on what kind of charges? Positives. Terminate on negative charges. The direction of the electric field at a point is what did we just say? Tangent to the field line. And let's look at the drawing. Which regions do you think have the strongest electric field? And which regions do you guess would have the weaker electric fields? And how could we tell by looking at the drawing? We haven't really talked at all about electric fields other than to say that we use the lines, to help represent how charges interact. What's that? Well, these are really continuous lines. So they're going from, right, there's some lines that go here, and there's some that loop all the way around over to here, right? But they start on, at any given point, you're right, you could draw a vector tangent to that line, and the length of that vector could be proportional, probably should be proportional to the strength of the field there. I agree with that. But from this diagram, where do you think the electric field might be strongest? Close to the charges, right? And as you move away from the charges, it would maybe drop off. So what feature of this drawing would indicate changes, with proximity to those charges? It's almost like if you've done any hiking, use a topographical map. Yeah, the density of the lines. Similar. It's a little different, but similar. It's in that respect, it's similar. That the density of the field lines. So in this region here, where there's a lot of, if you were to draw a box, a certain dimensions here, and you draw the same dimension box here, you'd have less field lines going through your box out here than you have in here. So the density of the field lines is stronger where the electric field is stronger. And when you noticed when I drew it, for just a spherically symmetric charge distribution, those lines are going radially outward in the spherical direction. So they're naturally going to get further and further apart as we move away. So you see the electric field's dropping off as we move away from that charged object. So the magnitude of the electric field is greater in regions where the field lines are more dense. Another property not apparent from the drawing below, maybe it is apparent. Well, they didn't tell you, I guess. We don't know what those charges are yet. Is that the number of field lines that originate on a positive charge or terminate on a negative charge, the number of lines is proportional to the magnitude of the charge. So how many lines are coming out of that top positive charge? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. How many are coming out of the bottom positive charge? Same number. So those two charges have the same magnitude. If one of them is 4 coulombs, the other one is 4 coulombs. How many for the middle one? Yeah, they didn't draw this correctly. Yeah, there should be 24. I'll show you why. Because they drew these two curved like this. You see that? So where's this curved one going to go? It's going to loop way out, and it's going to come back and come in at a slight angle here. So they should have had two, one coming in at a slight angle and one like they did on the opposite side. Did they do? Where's the opposite side? Yeah, this is actually drawn better. Count the lines on this one. We've got 12 at the positive, right? And we have 24 on this negative. This is drawn correctly. So this one would actually loop way out and then come back in over here. And so this would be, if this was 4 and this was 4, this would be 8. Because it has twice as many field lines that originate on it. All right, so the number of field lines that originate or terminate on a charge is proportional to the charge, the magnitude of the charge. So those are our basic rules for electric field lines. And let me tell you what the electric field is. Just real quickly. What we want to do is take away, we did a very similar thing with gravity. We got tired of doing this. Every time we wanted to calculate the weight of something, every time we wanted to calculate the weight of something on the surface of the Earth, we got tired of this G m1 m2 over r squared, where m1 is the mass of the Earth, m2 is our object of interest, and r squared is the radius of the Earth squared. We got tired of doing that calculation every time. So we said, let's just define a gravitational field that exists on the surface of the Earth and say that the gravitational field is the force divided by the mass that we're interested in. And what is that? It's g m Earth over r Earth squared, and we know that that's 9.8, right? And then, what do? Every time we want to figure out the force, we multiply the mass of interest times the gravitational field, and that gives us the force. And we're going to do the same with electricity. We're going to say the electric field is the force divided by one of the charges. Because what is the force? It's k q1 q2 over r squared, right? So we can divide by the charge that's at the location where we want to know what the electric field is. And we can then determine the electric field from all the other charges. So for a point charge, what is the electric field? Because we've taken F and divided it by one of the charges, and that's what we're left with. So the electric field and the force, those are vector quantities. The electric field points in the same direction as the force if Q is positive. If Q is negative, it changes, it flips the direction. Another way of writing this is F is equal to QE. And that's what I've written here, right? F equals mg, or F equals QE. So we can determine an electric field, and then from the electric field we can multiply by a charge to get the force. And this is something that is independent of whatever charge is sitting at that location, right? You can figure out the electric field based on all the other charges in your problem. All the other charges in your problem contribute to the electric field at that location. Then whatever charge you stick at that location, you just multiply it by Q to figure out the force. That's kind of what we did here. We figured out the gravitational field due to the Earth, and then whatever mass we stuck into this equation gave us the force of gravity acting on that one object.